Stars are born, they shine, and one day they collapse. But what really happens when a star's life ends in gravity's final act? In this video, we'll explore the science of stellar collapse from fading giants to cosmic explosions. If you enjoy this journey, please like, subscribe, share, and tell us in the comments what cosmic mystery you'd like us to explore next. Thank you for being here. Now, let's begin. A massive star spends most of its lifetime quietly fusing hydrogen into helium in its core. For millions of years, this process continues in steady balance, with gravity pulling inward and the heat of fusion pushing outward. Over time, the hydrogen in the central region runs out, and the star adjusts by contracting slightly. This contraction raises the temperature and allows the fusion of helium into heavier elements such as carbon and oxygen. With each stage of exhaustion and ignition, the star builds a new layer around the core. What begins as a simple structure with a hydrogen-burning center becomes increasingly complex, forming a nested set of shells where different reactions occur at different depths. In the final stages of life for a star much more massive than the Sun, the interior resembles a layered onion. At the center sits a growing core of heavy elements. Around it are concentric shells, where helium fuses into carbon-carbon, into neon-neon, into oxygen into silicon, and silicon eventually into iron. Each shell is powered by heat released when lighter nuclei join to form heavier ones. These reactions release energy only up to a certain point, and each new layer burns through its available fuel more quickly than the last. Hydrogen fusion may last millions of years, helium fusion only a fraction of that, and the fusion of silicon into iron can take just days. The surrounding shells are dense and hot, but the inner core holds the greatest weight. Gravity squeezes the central regions, and the outer layers rest upon it like a stack of blankets pressing down. The deeper one goes inside the star, the higher the pressure becomes. Under these conditions, matter behaves differently than it does on Earth. At such extreme density, the atomic nuclei are packed tightly together, and the electrons are forced into close proximity. The particles jostle in a way that no ordinary material on Earth can imitate. Yet the processes still follow the same physical laws. In this layered interior, there is no sharp boundary like the surface of a planet. Instead, one region blends into the next with gradual changes in temperature, density, and composition. The layers behave almost like distinct furnaces, each producing energy that helps support the weight of the star above it. Yet despite the steady outward flow of energy, the balance grows fragile. Every new shell that forms marks a step toward instability. The reactions become more intense, but their duration shortens drastically. This acceleration is an unavoidable sign that the star is nearing the end of its fuel supply. The core of heavy elements does not produce energy in the same way as the outer shells. Iron in particular is different from lighter elements such as hydrogen, helium, or carbon. When iron nuclei are formed, the process does not release energy. Instead, it consumes it. Fusion of iron cannot provide the outward push needed to counter gravity. As the innermost regions fill with iron, the star builds a dead weight at its heart. Around this iron center, the shells continue to operate briefly, but they cannot prevent the eventual collapse that is set into motion by the accumulation of material that no longer contributes energy. To understand the star at this stage, one can imagine the pressures involved. The densities in the core rise to many times that of ordinary matter. A spoonful of such material would weigh as much as a mountain. The temperature climbs to billions of degrees, far beyond what is found in any normal setting. Radiation floods the interior, and neutrinos begin to slip through the dense matter, carrying energy away. Yet all of this activity is confined inside the star, hidden beneath the outer envelope that still appears as a luminous surface to an outside observer. To a telescope, the star might still shine in much the same way it did before, but within it is fundamentally transformed. In these moments, the balance of forces is still holding. Gravity presses inward while the heat and pressure from fusion in the outer shells push outward. But the center is quietly shifting. Each second that passes allows more iron to accumulate. Each second also brings the star closer to a condition where no further fusion can halt the inward force. The process is slow on the human timescale, but swift on the timescale of a star's life. What once took millions of years now unfolds in thousands, then hundreds, then days. The great luminous body is racing toward its end without any sign visible to the outside. If one could look directly into the star at this stage, the sight would be remarkable. There would be a dark inner sphere of iron at the very center, dense and inert, surrounded by layers of glowing plasma, where lighter elements are still fusing. Each shell would pulse with its own rhythm, adding its contribution of energy while feeding ash into the regions below. The whole structure would resemble a nested series of fires, each burning at different intensities stacked one upon another. The matter between shells would not be empty. It would be crowded with ions, electrons, and radiation flowing ceaselessly as the star strives to maintain equilibrium. Although hidden from view, the conditions in this deep interior are known through theory, through laboratory physics, and through indirect evidence from supernova remnants. Models confirm that the onion-like structure is a consistent outcome of stellar evolution for stars more massive than about 8 times the Sun. These models rely on principles tested in particle accelerators and nuclear reactors on Earth, where scientists measure the behavior of atomic nuclei and use that data to calculate what occurs under much greater pressures. Every observed supernova remnant, every spectrum of light that carries the imprint of heavy elements supports this understanding of how massive stars reach their final configuration. In the calm rhythm of astrophysics, this stage is not sudden. The star spends long periods in apparent stability, even while its core is undergoing irreversible changes. The outer layers remain luminous, radiating into space as they always have. To any distant observer, the star would look like countless others shining steadily in the night sky. Yet inside, the slow accumulation of iron marks the beginning of collapse. The quiet, step-by-step construction of shells and core brings the star toward the threshold, where gravity will claim its final victory. This is the setting a massive star layered like an onion, with each fusion shell marking a chapter in its long story. The outer regions still shine, but the center is heavy and inert. The balance still holds, but the margin is shrinking. The star is prepared silently for the collapse that physics dictates must come once the fuel is gone. The stillness of the present interior hides the inevitability of what follows, but for now the picture is simply that of a layered structure, dense and hot, resting under the weight of its own gravity and the last stages of its nuclear fire. Inside a massive star that has built up an iron core, the processes that once supplied energy now reach a firm limit. Fusion depends on the principle that when light nuclei combine to form heavier ones, the mass of the new nucleus is slightly less than the total mass of the parts. That missing mass becomes energy, and it is this energy that produces the radiation pressure needed to hold a star against gravity. With elements up to iron, the binding energy per nucleus increases, so fusion produces an excess of energy that sustains the star. But with iron, the curve of nuclear binding reaches its peak. Adding particles together no longer gives off energy but requires it. That means the core made of iron and nearby elements cannot generate the heat and pressure required to push outward. The star has entered a new regime where its heart produces no further fuel to resist collapse. The shells surrounding the iron core continue to operate briefly. Silicon burns into iron at staggering rates, producing fresh nuclei in just days before the fuel is gone. Above that, oxygen, neon carbon, helium and hydrogen still burn in layers, each providing its own support. Yet these outer shells are only temporary buffers. They cannot compensate for the growing dead mass at the center. Gravity presses without pause, and without fusion at the core, there is nothing left to counter the inward pull. The balance that kept the star stable across millions of years is broken by a single fact. Iron cannot yield energy through fusion. The star does not collapse instantly the moment iron appears. Instead, the iron core grows steadily. It accumulates through the ash of silicon fusion and through the byproducts of other shell reactions. Each new layer of silicon burning adds to the mass of the inert center. Over time, the iron core reaches masses comparable to that of the Sun itself, compressed into a sphere the size of Earth. The density is immense, billions of times greater than the density of water. Matter in this state is not like rock or metal as we know it. Atoms are stripped of their electrons, nuclei are crowded so closely that their boundaries blur, and electrons are squeezed into a degenerate gas that resists compression, not through heat, but through the quantum principle that identical particles cannot occupy the same state. This quantum mechanical resistance is what allows the iron core to temporarily exist without collapsing further. At this point, a new form of pressure takes center stage: electron degeneracy pressure. Unlike the thermal pressure of ordinary gases, electron degeneracy pressure does not depend on temperature. Even as the core radiates heat and cools, this pressure remains. It arises from the exclusion principle, which states that no two electrons can share the same quantum state. In dense matter, electrons are forced into higher and higher energy levels, and that built-up pressure supports the core. For a time, this stabilizing effect halts the collapse, but degeneracy pressure has a strict limit. When the mass of the core exceeds about 1.5 times that of the Sun, known as the Chandrasekhar limit, no further arrangement of electrons can resist gravity. The core is then destined to fall inward. This progression toward collapse illustrates a profound interplay between the micro and the macro. On one side is the quantum world of electrons ruled by principles that govern the smallest particles. On the other side is the astrophysical scale of stars ruled by gravity that acts across millions of kilometers. The fate of a star depends on how these two extremes balance. So long as the core mass is less than the Chandrasekhar limit, electron degeneracy pressure is enough. A star of lower mass may end its life quietly as a white dwarf supported indefinitely by this pressure, but when the iron core of a massive star continues to grow, surpassing the threshold, this stabilizing force is overwhelmed. At the moment when the iron core nears this critical mass, changes accelerate. The temperature rises not because fusion produces energy, but because the core is squeezed more tightly. Photons inside the star reach energies high enough to disassemble atomic nuclei. This process is called photodisintegration. A single high-energy photon strikes an iron nucleus and breaks it into smaller pieces such as helium nuclei and free neutrons. Instead of adding energy to the star, this reaction consumes it. Each breakdown removes thermal energy from the core and robs the star of pressure support. The effect is destabilizing. The very radiation that once balanced gravity now contributes to collapse. Along with photodisintegration comes another effect that hastens the process. As the density increases, electrons are captured by protons, forming neutrons and releasing neutrinos. This process reduces the number of electrons available to provide degeneracy pressure. With fewer electrons, the core loses even more of its resistance to compression. The neutrinos produced in vast numbers escape almost freely, carrying away energy at a rate unmatched by any other mechanism. In just seconds, the energy budget of the core is drained. What began as a steady build-up of iron turns into a runaway chain of events that cannot be halted. From the outside, the star may appear little changed at this moment. Its surface still glows with the heat from the outer shells, and its brightness does not immediately betray the turmoil within. But deep inside, the physical state of matter is changing irreversibly. Atomic nuclei are disintegrating, electrons are vanishing into protons, neutrinos are streaming outward at nearly the speed of light and pressure, support is failing. The star has crossed the boundary from which there is no return. Collapse is no longer a distant outcome. It is an active process unfolding in fractions of a second on the scale of the core, even while the exterior still shines steadily in space. To understand why iron plays this pivotal role, one can look again at the chart of nuclear binding energies. Light nuclei such as hydrogen and helium gain energy when they combine, which is why stars shine for so long. Heavy nuclei beyond iron release energy when they split, a process known as fission. But iron sits at the boundary with no energy to yield either way. Fusion beyond it consumes energy rather than producing it. Thus, once a star builds an iron core, it has manufactured the very element that seals its fate. The balance of billions of years collapses because of a single principle. Fusion can no longer provide the outward push. This situation is not conjecture, but well grounded in evidence. Supernova remnants show high abundances of iron and nickel, supporting the conclusion that these elements dominate the core before collapse. Laboratory physics confirms the energies involved in nuclear reactions, and astrophysical models show the same runaway processes of photodisintegration and electron capture. The pattern is consistent across multiple lines of observation and theory, forming a clear picture of how massive stars move from stability to collapse. The exhaustion of nuclear fuel in a massive star is therefore not just a gradual dimming, but a shift in the very forces that govern matter. The shells still glow with fusion, but the central heart is inert. Quantum pressure tries to hold the core, but beyond a fixed mass it fails. Energy that once supported the star is drained away by processes that consume rather than provide. And when that point is reached, collapse begins in earnest, marking the end of equilibrium and the start of a new violent stage in the life of the star. As the iron core of a massive star grows heavier, the role of electron degeneracy pressure becomes more apparent. This pressure does not rely on heat, as an ordinary gas would, but instead on a fundamental principle of quantum mechanics. The exclusion principle states that no two electrons can occupy the same quantum state. When matter is compressed to extremely high densities, electrons are crowded into all available energy levels. The result is a pressure that pushes back against further compression even when temperatures fall. It is this property that allows a white dwarf star, which is the remnant of a less massive star, to exist in a stable state for billions of years. For a time, this same effect also slows the collapse of the iron core in a massive star. However, there is a strict mass limit to how much support electron degeneracy pressure can provide. If the core remains under about 1.5 times the mass of the Sun, electron degeneracy pressure can hold it up indefinitely. This threshold is known as the Chandrasekhar limit, named for the astrophysicist who calculated it. If the mass grows larger, the electrons are forced into such high energies that gravity still wins. The collapse becomes unstoppable. This limit is not an arbitrary figure. It comes from precise calculations of how quantum mechanical forces balance gravitational pressure. For stars, this distinction separates two very different endings. Below the limit, a star may become a quiet white dwarf. Above it, a massive star progresses toward catastrophic collapse. In the center of an evolving massive star, the iron core steadily approaches this limit. Silicon fusion continues just above the core, feeding more iron ash into the central region. With each passing moment, the mass grows. The electrons already resist strongly, but when the core mass crosses the critical threshold, the conditions change sharply. Electrons are forced into higher momentum states, and eventually the energy of these states becomes great enough that electrons can combine with protons producing neutrons and neutrinos. This process, called electron capture, reduces the number of electrons available to provide degeneracy pressure. The fewer the electrons, the less support the core has against gravity. The creation of neutrinos in this stage is significant. Neutrinos are extremely light particles that interact only weakly with matter. Unlike photons, which scatter many times inside a dense star before escaping, neutrinos pass through most matter with almost no interaction. As electrons are captured by protons, neutrinos are released in vast numbers. They stream away at nearly the speed of light, carrying energy directly out of the star. This rapid energy loss cools the core, making it even less able to resist gravity. The combination of reduced degeneracy pressure and lost thermal energy accelerates the inward motion. The picture that emerges is one of a core that becomes progressively less stable as more processes take energy away. Photodisintegration consumes photons that once added pressure. Electron capture reduces the pool of electrons that provided quantum resistance. Neutrinos drain energy from the system without obstruction. Each effect pushes the balance further toward collapse. Once the Chandrasekhar limit is exceeded, no known mechanism can restore equilibrium. Gravity takes control and the fall inward gathers speed. It is important to consider why the Chandrasekhar limit is fixed at the value it is. The figure of about 1.5 times the mass of the Sun comes from the relationship between the mass of the star, the density of electrons, and the energy states those electrons occupy. At low densities, electrons can occupy low energy states, and degeneracy pressure is small. As density increases, electrons are forced into higher states, raising the pressure. But beyond a certain point, the momentum of the electrons becomes so great that adding more mass only increases the gravitational force faster than the degeneracy pressure can rise. This tipping point is inevitable, and it is set by the constants of nature. In a real star, when the iron core grows beyond this limit, collapse is guaranteed. While the Chandrasekhar limit explains the point of no return for massive stars, it also accounts for the long-term stability of smaller stars. Our Sun, for example, will never build a core massive enough to exceed this threshold. It will eventually leave behind a white dwarf with a mass less than the limit supported indefinitely by electron degeneracy pressure. For stars with 8 or more times the mass of the Sun, however, the iron core does surpass this critical value. In those cases, collapse begins as soon as the Chandrasekhar limit is crossed. When collapse begins, it happens quickly. The core, no longer able to resist gravity, contracts in a fraction of a second. The densities increase from billions to trillions of times the density of water. Protons and electrons combine into neutrons almost everywhere, producing a dense ball of nuclear matter. The neutrinos generated in this process flood outward, carrying away more energy than all the photons the star has ever radiated in its life. The scale of these numbers is vast, but the underlying principle remains simple. Gravity overcomes all other forces when the Chandrasekhar limit is passed, and collapse cannot be halted until a new form of matter provides resistance. This understanding is not theoretical alone, but grounded in observation. Astronomers have measured the masses of white dwarfs and found none above the Chandrasekhar limit. This consistency confirms that electron degeneracy pressure has a well-defined maximum. Supernova remnants show signatures of collapsed cores that match the predictions of models where the Chandrasekhar limit is exceeded. Neutrino detections from the supernova in 1987 provided direct evidence that electron capture and neutrino outflow occur during collapse. Together, these data anchor the theoretical framework in observed reality. It is striking that the fate of a massive star is determined by such a precise balance. The Chandrasekhar limit acts like a boundary drawn by the laws of physics. On one side of the line, stars end in quiet white dwarfs, that may cool for trillions of years. On the other side, they collapse violently, creating neutron stars or black holes. The difference depends only on mass, but that difference changes the outcome from stability to catastrophic implosion. In this way, the Chandrasekhar limit represents not just a number, but a dividing principle in stellar evolution. At the stage of collapse, the star does not choose. The outcome is written in the growth of its iron core. If the mass remains below the limit, degeneracy pressure wins. If the mass passes above, gravity wins. In a massive star, the latter is inevitable. The shells above continue burning, the surface still glows, but the core is already crossing the boundary. The quantum pressure of electrons, which seemed so strong for a time, now reaches its end. In moments, the star moves into a phase where neutrons rather than electrons become the dominant form of matter, and the collapse pushes onward into realms even denser than before. At the center of the collapsing star, the buildup of iron reaches its unavoidable consequence. Iron is a nucleus with the highest binding energy per particle, which means that no rearrangement of its protons and neutrons through fusion can release additional energy. Fusion beyond iron requires energy input rather than providing output, and so the star loses its ability to produce the radiation pressure needed to counter gravity. Once silicon fusion completes in the surrounding shells, the core is left as a heavy mass of iron group elements. In this state, the star is effectively carrying a dead weight that only adds to the gravitational pressure pulling inward. When photons within the hot interior reach extremely high energies, they begin to break apart the iron nuclei in a process called photodisintegration. A single photon can strike an iron nucleus and shatter it into smaller fragments, such as helium nuclei and free neutrons. Instead of supporting the star, this process consumes the energy of the photon. The effect is destabilizing, as thermal energy that once added pressure is now spent breaking apart nuclei. This creates a feedback loop. The more the core contracts, the higher the photon energies become, and the more photodisintegration occurs, which further reduces the thermal support. As collapse continues, electrons are also forced into close proximity with protons. Under such extreme densities, they combine to form neutrons and release neutrinos. This process is known as electron capture. It removes electrons from the matter, reducing the electron degeneracy pressure that had been resisting gravity. Each electron that disappears into a neutron leaves less support for the core. At the same time, the neutrinos produced escape almost immediately, carrying energy away from the system at extraordinary rates. In just seconds, the core loses more energy through neutrinos than it has radiated in light during its entire existence. The combined effect of photodisintegration, electron capture, and neutrino escape drives the core into a rapid implosion. The collapse is not slow or gradual once this point is reached. It unfolds in less than a second. The material falls inward at a significant fraction of the speed of light. As the density climbs, matter reaches states normally found only in atomic nuclei. Protons and neutrons are squeezed so closely together that they form a uniform fluid of nuclear matter. This is the threshold where a new type of pressure arises called neutron degeneracy pressure, which can momentarily halt the collapse. The sudden stop of the inner core against this neutron barrier creates a shock wave that moves outward. But before that stage, the inward journey itself is remarkable. The core contracts from the size of Earth down to a sphere just a few tens of kilometers across. In this brief collapse, the gravitational energy released is immense. Most of it escapes in the form of neutrinos, but the mechanical effect on the star is profound. The outer shells, still burning, suddenly lose their support and begin to fall inward as well. The entire star is now caught in the motion, with layers collapsing toward the center. The photodisintegration process continues in the inflowing material. Each photon that breaks apart a nucleus consumes energy, and this consumption increases the instability. The iron that once represented the most stable possible nucleus has become the seed of collapse, because the star can no longer use it for fusion and must instead endure its disassembly. Each broken nucleus increases the fraction of free neutrons and helium nuclei within the core, and each event removes more of the thermal support. This cascade accelerates the implosion, drawing everything inward. Observational evidence supports this picture. When astronomers study the remnants of supernovae, they find abundant elements heavier than silicon with iron and nickel dominating. These signatures are consistent with models showing that the last stage of fusion produces iron which then undergoes photodisintegration. The light curves of supernovae often show late-time brightness powered by the decay of nickel into iron, further confirming that these elements were abundant in the core before the explosion. The agreement between models and observed spectra lends strong support to the idea that photodisintegration is central to the process of collapse. The role of neutrinos is particularly important to emphasize. They are not only byproducts of electron capture, but also carriers of energy that escape almost freely. In an ordinary star, photons take thousands of years to migrate outward from the core to the surface. Neutrinos, by contrast, pass through matter with minimal interaction. In the collapse phase, they leave the core in seconds, draining energy directly. This rapid escape accelerates the implosion and contributes to the loss of equilibrium. Without neutrinos, the collapse would proceed differently, but in reality they dominate the energy flow. Measurements of neutrinos from the 1987 supernova in the Large Magellanic Cloud confirmed this aspect of theory. Detectors on Earth registered a brief burst of neutrinos arriving just before the visible explosion, providing direct evidence of these processes inside the collapsing star. Inside the core during collapse, matter no longer behaves as it does under any normal condition. Nuclei break apart, protons turn into neutrons, and radiation energy is converted into fragments. The densities reach a point where even the concept of atoms ceases to apply. Instead, there is a dense fluid of neutrons, electrons, and small nuclei, all compressed into a space that shrinks dramatically in fractions of a second. The scale of change is staggering. A sun-sized mass implodes to a region only a few tens of kilometers across in less than one heartbeat. For now, the focus remains on the collapse itself before the shockwave forms. This is the point where the star undergoes the irreversible transition from stability to implosion. Every force that once held back gravity is neutralized. Photodisintegration consumes energy, electron capture removes electrons, neutrino escape drains heat, and degeneracy pressure is overcome. Gravity, the one force that never weakens with distance inside the star, dominates completely. The core falls layer after layer inward to densities beyond ordinary nuclear matter. From the perspective of astrophysical theory, this stage marks the clean break between a star that shines through nuclear fusion and a star that collapses under its own gravity. The onset of photodisintegration is like a switch. Once photons reach sufficient energy, the reaction begins, and once it begins, it cannot be reversed. Each nucleus destroyed requires more energy input, which leads to more collapse, which raises temperatures further, which creates more destructive photons. It is a feedback loop that ensures total failure of equilibrium. This is why the collapse of massive stars is so sudden compared to their long lifetimes. The physics of this stage is secure in principle and in evidence. Laboratory experiments replicate nuclear binding energies and photon interactions, confirming the thresholds for disintegration. Neutrino physics, though difficult to measure directly, is well established through both particle experiments and astrophysical detections. The overall picture is consistent. A core dominated by iron cannot resist gravity, because the very processes occurring inside it remove pressure support. Collapse follows, inevitably marking the transition from a star that once lived through fusion to a remnant that must find stability in a new form of matter. As the collapse accelerates, the star reaches conditions where ordinary matter is transformed into something altogether different. The core, once a dense collection of iron nuclei, is now reduced to a mixture of neutrons, protons, electrons, and small fragments. Gravity squeezes this mixture inward at an extraordinary rate. Within less than a second, the core shrinks from the size of Earth to a sphere only a few tens of kilometers across. The infall is so fast that the inner regions and the outer regions behave differently. The very center of the core halts, first reaching densities where neutrons are packed tightly together while the layers above it are still plunging inward. This difference in motion creates a sudden and violent effect the core bounces. The bounce occurs when neutron degeneracy pressure arises. Just as electrons resist being forced into the same quantum states, neutrons also follow the exclusion principle. At densities several times greater than those of atomic nuclei, the neutrons can no longer be compressed further. They resist with extraordinary force, halting the collapse of the inner core almost instantly. The material that was still falling inward strikes this neutron-rich center, and the sudden stop produces a shock wave that travels outward through the infalling layers. This shock is the seed of the event that observers later see as a supernova. Yet the story is not as simple as a single bounce leading to an explosion. The shock forms, but it quickly encounters enormous resistance. As it pushes outward, it must plow through the still collapsing material above. Every layer of iron nuclei it encounters is subject to photodisintegration, which consumes energy. Each nucleus broken apart robs the shock of momentum. At the same time, neutrinos continue to flood outward, carrying away even more energy. The result is that the shock stalls after advancing only a few hundred kilometers. Instead of blasting the star apart, it falters trapped within the dense environment. This stalling of the shock is a central challenge in the theory of stellar collapse. If nothing else intervened, the shock would simply fizzle out, and the outer layers would continue falling inward. The star would collapse completely into a black hole without any visible explosion. But observations show that many massive stars do explode as supernovae, leaving behind brilliant displays and heavy element debris. This means that something must revive the stalled shock. The leading explanation involves the very neutrinos that initially drained the energy. Though most neutrinos pass through matter without interaction, a small fraction are absorbed in the dense region just above the neutron core. Because the number of neutrinos is so enormous, even this tiny fraction deposits a large amount of energy. Over a period of seconds, this heating can re-energize the shock, pushing it outward once again. This neutrino-driven revival is still the subject of active research. Computer simulations have shown that under certain conditions, neutrino heating is sufficient to reignite the shock and drive it outward through the star. In addition, turbulence and convection in the hot layers may assist by helping distribute the deposited energy more effectively. These processes are complex, involving fluid dynamics, particle physics, and radiation transport, all acting together in an environment beyond any laboratory experiment. But the broad picture is consistent. The collapse of the core produces a flood of neutrinos, and a portion of that energy is recycled to power the explosion. The physics of the bounce itself is remarkable. When the inner core reaches nuclear density, the transition to neutron matter happens almost instantly. The neutrons form a uniform fluid with properties unlike anything found on Earth. The pressure that arises in this fluid is sufficient to resist further collapse, at least temporarily. The size of the neutron-rich core is only tens of kilometers across, but it contains more mass than the Sun. The surface gravity of such an object is so intense that even light would be redshifted as it escapes. Yet at this stage it is not yet a stable neutron star. The explosion has not carried away the outer layers. As the shock is re-energized, it pushes outward again. This second phase is slower than the initial bounce but far more consequential. The shock gains strength from neutrino heating and from the accumulated pressure of hot matter behind it. Eventually it begins to move through the infalling outer shells. As it does, it transfers its energy to them, halting their inward motion and accelerating them outward. This is the beginning of the visible supernova. Within seconds, the star's interior is transformed from implosion to explosion. The outer layers that once pressed down with relentless weight are now hurled outward into space. The timescales of these processes are astonishingly short compared to the long life of the star. The burning of hydrogen lasted millions of years. The burning of helium and heavier elements lasted thousands to hundreds of years. But the collapse and bounce occur in less than a single second, and the shock revival happens over just a few more seconds. In that tiny fraction of the star's lifetime, the entire structure is overturned. The interior becomes a neutron-rich remnant while the exterior is expelled at thousands of kilometers per second. Evidence for the bounce and shock revival comes indirectly from supernova observations. The light curves of these explosions show a rapid rise in brightness, consistent with a sudden energy release. The spectra reveal heavy elements that must have been forged deep inside and then expelled. The detection of neutrinos from the 1987 event provided confirmation that enormous neutrino emission accompanies collapse. Simulations that include shock formation stalling and neutrino heating reproduce the broad features of these observations, even if the precise details remain a challenge. It is important to note that not all collapses succeed in producing an explosion. Some very massive stars may not revive the shock strongly enough. In those cases, the collapse continues and the entire star falls inward to form a black hole directly. The distinction depends on the mass of the star, the dynamics of the shock, and the effectiveness of neutrino heating. Thus, while the bounce and shock are universal features, their outcomes vary. Some stars explode brilliantly, while others vanish quietly into black holes. At this stage of description, the key image is of a core that has collapsed to neutron densities rebounded to create a shock stalled under the weight of infalling matter and then been revived by neutrino heating. The outcome is an expanding shock wave that carries the energy of the collapse outward. Around it, the outer shells are caught up in the blast. Within seconds, the fate of the star is decided. The center remains compact and dense, while the exterior is ejected in an explosion that may outshine an entire galaxy for a short time. The collapse and bounce are therefore the hinge point of stellar death. Before them, the star is an equilibrium of fusion and gravity. After them, the star is either a compact remnant surrounded by an expanding shell, or a black hole swallowing all that remains. The forces at work are not visible to the eye, but the physics is clear. Gravity overwhelms all until neutrons resist, and the sudden halt sends a shock that changes everything. Once the shock wave forms and stalls inside the collapsing star, the fate of the explosion depends on how energy is redistributed in the dense environment. The stalled shock is located only a few hundred kilometers above the surface of the newly formed neutron-rich core. In this region, conditions are extreme. The densities are close to nuclear levels, the temperatures reach billions of degrees, and matter exists as a seething mix of free neutrons, protons, electrons, and small atomic nuclei. Radiation pressure is enormous, but so is the weight of the infalling outer layers. The shock cannot continue outward unless some new source of energy is delivered into this dense zone. The main candidate for that energy is the immense stream of neutrinos produced by electron capture and other nuclear processes during collapse. Nearly all of the gravitational energy released when the core shrinks is carried away by neutrinos. The total energy of this neutrino flood is vast, more than enough to power a supernova, but only a small fraction of it needs to be deposited behind the shock to revive it. Neutrinos normally pass through matter with little interaction, but the densities near the neutron core are so high that a small but significant percentage are absorbed. Each absorbed neutrino transfers energy into the surrounding material, heating it and raising the pressure. Over the course of seconds, this heating can accumulate enough to restart the stalled shock. The mechanism is not purely one-dimensional. Simulations show that turbulence and convection in the region behind the shock play a critical role. Instead of energy being spread evenly, bubbles of heated material rise and mix with cooler regions, helping to distribute the neutrino energy more effectively. In some cases, large-scale instabilities such as standing accretion shock instabilities create sloshing or spiral motions that further stir the material. These multidimensional flows allow the neutrino energy to be used more efficiently than if the matter remained static. The combined effect is that the stalled shock can be pushed outward again slowly at first, then with increasing momentum. As the shock begins to move outward, it encounters the dense layers of the star's interior. Each layer it passes through resists with inertia and with photodisintegration that consumes energy. But the continued heating from neutrinos and the pressure from the hot matter behind the shock keep driving it forward. Once the shock passes a certain radius, the density of the overlying layers decreases rapidly and the resistance falls. The outward motion accelerates and the explosion becomes inevitable. The infalling material is reversed, turned from a collapsing shell into an expanding envelope. The revival of the shock through neutrino heating is supported by several lines of evidence. The neutrino burst detected from the supernova of 1987 was consistent with models predicting the release of gravitational energy in the form of neutrinos. The timescale of the burst, lasting several seconds, matches the duration over which neutrino heating would act to re-energize the shock. In addition, the observed distribution of heavy elements in supernova remnants supports the idea that convection and turbulence played roles in mixing the material, a signature of multidimensional dynamics in the explosion mechanism. The physics of the shock revival is still an active area of research. Some computer models succeed in producing explosions, while others show failures depending on the details of neutrino transport and fluid motion. This uncertainty reflects the complexity of the problem, which combines nuclear physics, particle interactions, radiation transfer, and hydrodynamics on scales ranging from subatomic to stellar. Nevertheless, the consensus is that neutrino heating is the essential ingredient that allows the stalled shock to resume its outward journey. Without this process, the majority of observed core collapse supernovae could not be explained. Once the shock is revived, the rest of the star's fate is determined. The outer layers, still collapsing inward, now encounter a wall of energy moving outward. The collision reverses their motion and launches them away from the core at thousands of kilometers per second. The amount of mass expelled depends on the initial size of the star, but it is typically several times the mass of the Sun. The ejected material carries with it the products of nuclear burning from the star's lifetime, along with new elements forged in the explosion itself. These elements are dispersed into space, where they eventually become part of interstellar gas clouds that may later form new stars and planets. The neutrino-driven mechanism also has implications for what remains at the center. If the explosion is strong enough, the core settles into a neutron star supported by neutron degeneracy pressure and other nuclear forces. If the explosion is weaker, or if the star was especially massive, some of the ejected material may fall back onto the core, adding mass. In that case, the remnant may collapse further into a black hole. The balance between explosion strength and stellar mass determines which outcome occurs. From the perspective of an outside observer, the processes of neutrino heating, convection, and shock revival are hidden. The star's surface does not reveal what is happening deep inside until the shock finally reaches the outer layers. When it does, the release of energy is immense. The star brightens dramatically, often outshining an entire galaxy for weeks. The visible light is only a small fraction of the total energy released, but it is enough to mark the death of the star across vast distances in the universe. The interior picture remains crucial, though. Without the transfer of energy from neutrinos to the stalled shock, the explosion would not occur. This shows how the fate of a star hinges on particles that interact so weakly with matter that trillions of them pass through Earth every second unnoticed. In the environment of a collapsing star, however, their collective effect is decisive. The delicate balance of how many neutrinos are absorbed, how convection redistributes the heat, and how turbulence shapes the flows determines whether a supernova will succeed or fail. It is a striking example of astrophysics where the smallest scales and the largest scales are directly connected. Subatomic interactions between neutrinos and nucleons influence the fate of entire stars and the enrichment of galaxies with heavy elements. The neutrinos carry away most of the collapse energy, but the small portion they leave behind is enough to drive some of the most energetic explosions in the universe. The revived shock that emerges from this process is not just a wave of energy, but the mechanism that ensures the death of one star contributes to the birth of future generations of stars and planets. At this stage, the star has passed the point of no return. The iron core has collapsed, the neutron core has formed, the shock has stalled, and neutrinos have breathed life back into it. The outward blast is now moving through the star-accelerating layers of matter into space. The dense core remains poised to become either a neutron star or a black hole, while the outer layers are destined to enrich the cosmos with new material. The cycle of stellar death and renewal proceeds guided by the physics of neutrinos' quantum pressure and gravity. While neutrinos dominate the energy release during core collapse, their role extends beyond simply carrying energy away. They also shape the dynamics of the explosion. As the outward shock wave struggles to gain momentum, the constant stream of neutrinos continues to interact with the matter around the proto-neutron star, the dense remnant left at the center. Although most neutrinos pass freely through matter, the sheer number produced during collapse is so large that even a small probability of interaction becomes significant. In the dense zone just above the neutron-rich core, neutrinos deposit energy that creates a heated region called the gain layer. This gain layer is crucial because it provides the pressure needed to push the shock outward again after its initial stall. Neutrino heating is a delicate process. If the heating is too weak, the shock cannot revive and the star continues to collapse into a black hole without a visible explosion. If the heating is strong enough, the shock regains momentum and expands outward through the infalling layers. The balance depends on many factors: the density of matter, the efficiency of neutrino absorption, and the turbulent flows that redistribute the heat. Convection within the gain layer mixes hot and cool regions, ensuring that energy does not remain trapped in one place. This mixing increases the efficiency of the heating and improves the chances of shock revival. The dynamics are not uniform but highly chaotic. Three-dimensional simulations show swirling flows, rising bubbles, and sloshing motions that alter the geometry of the explosion. These instabilities are not flaws in the models, but natural consequences of the conditions. Matter heated by neutrinos becomes buoyant and rises while cooler material sinks. This continuous circulation helps maintain the energy balance that allows the shock to grow. Some simulations also reveal spiral patterns caused by instabilities in the shock itself, further shaping the explosion. Though the details are still under study, the broad conclusion is clear: turbulence and convection are partners to neutrino heating in making supernovae possible. As the shock finally pushes outward through the star's layers, it begins to interact with material that has not yet been affected by collapse. The shock compresses, and heats these outer regions, triggering additional nuclear reactions. In these fleeting moments, the conditions are extreme enough to forge elements heavier than iron. Rapid neutron capture, known as the R process, occurs as abundant neutrons are available and captured by nuclei faster than they can decay. This process creates some of the heaviest elements in the periodic table, including gold, platinum, and uranium. Thus, the same explosion that destroys the star also seeds the galaxy with new building block for planets and life. The importance of neutrinos in this picture is supported by observation. In 1987, a supernova in the Large Magellanic Cloud provided the first direct detection of neutrinos from a stellar collapse. Underground detectors in Japan, the United States, and Russia recorded a burst of neutrinos lasting several seconds just before the light from the explosion reached Earth. The number and timing of these detections matched the predictions of models in which neutrinos carry away nearly all of the gravitational energy released during collapse. This was a milestone in astrophysics, confirming that neutrinos are not only theoretical participants, but real and observable messengers from inside collapsing stars. Theoretical work since then has expanded on this foundation. Simulations now include detailed neutrino transport with calculations of how neutrinos of different energies are absorbed, scattered, or escape. These models show that the balance of energy deposition is sensitive to small changes in conditions. A slightly more massive star may not explode because the shock is harder to revive, while a slightly less massive one may explode more easily. This sensitivity explains why some stars end in visible supernovae, while others collapse directly into black holes. The difference lies not only in total mass but in the interplay of neutrinos' convection and shock dynamics. The neutrinos that escape also carry information about the interior state of the star. Different processes produce neutrinos of different energies, and the spectrum of neutrinos detected can reveal details of electron capture, neutron formation, and thermal conditions. Although neutrino detection is challenging, each observed event provides a unique window into the otherwise hidden interior. Unlike light, which emerges after traveling through layers of gas, neutrinos travel almost directly from the core to the detector. They are direct messengers of the collapse itself. Future neutrino observatories are expected to provide much richer data, allowing scientists to probe these processes with greater detail. The outward-moving shock strengthened by neutrino heating eventually escapes the dense interior and begins to move through the less dense outer layers of the star. At this stage, neutrino interactions become less important as the density drops and fewer neutrinos are absorbed. By then, however, their work is done. They have re-energized the stalled shock, allowing it to progress into the envelope of the star. The layers above, which may include hydrogen and helium depending on the type of star, are accelerated outward at enormous speeds. Within hours to days, the shock reaches the surface and the star brightens dramatically as a supernova. From the perspective of stellar physics, the neutrino phase is the silent core of the drama. Observers see the bright light and expanding debris, but these are consequences of the processes driven deep within. Neutrinos, nearly invisible to detectors, are the real agents of transformation. They not only cool the core by escaping, but also heat the material just enough to reverse the collapse into an explosion. Without them, the majority of massive stars would end in quiet collapse to black holes, and the universe would lack much of its heavy element content. Reflecting on this stage, the balance between invisibility and influence is striking. Neutrinos are among the least interactive particles in the universe, yet in the unique environment of a collapsing star they decide the outcome of stellar death. Their presence links the quantum world of particle physics to the galactic scale of element production. The neutrinos carry away most of the gravitational energy they deposit, just enough to restart the shock, and they reveal the hidden processes to distant observers. In this sense, they are both the exhaust and the engine of supernovae, shaping the cosmos silently and decisively. At this point in the star's collapse, the picture is complete. A core transformed into neutrons, a shock stalled, and then revived a flood of neutrinos, carrying away the vast energy of implosion and a wave of heated material pushing outward through the star. The stage is set for the explosion to manifest visibly, but the true driver of the event remains the neutrinos' invisible particles that connect the inner core to the outer blast and the enrichment of the galaxy beyond. The moment of core collapse is marked by the overwhelming dominance of gravity. Once the Chandrasekhar limit is surpassed and electron degeneracy pressure fails, nothing can prevent the implosion until matter itself is compressed to nuclear densities. In less than a second, the inner core contracts from thousands of kilometers across to a compact region only tens of kilometers wide. The outer layers, still falling inward at high velocity, continue their plunge toward the center. The contrast between the halted inner core and the still collapsing outer material produces one of the most dramatic transitions in stellar physics. At the exact point where nuclear densities are reached, neutrons resist further compression through neutron degeneracy pressure and strong nuclear forces. The collapse of the inner core halts abruptly, and the infalling material crashes into this newly rigid neutron-rich surface. The collision creates a rebound effect, launching a shock wave that propagates outward. The shock forms quickly, but does not succeed in escaping the star immediately. Instead, it encounters resistance from two major processes: photodisintegration and continued infall of stellar material. Photodisintegration acts as a powerful energy sink. As the shock travels outward, it encounters iron nuclei and other heavy elements in the surrounding layers. The immense temperatures generated by the shock produce high-energy photons capable of breaking apart these nuclei into lighter fragments, such as helium nuclei and free neutrons. Each nucleus destroyed consumes a large amount of energy, draining the shock of its momentum. At the same time, the outer layers of the star, still collapsing inward, press down against the shock, further sapping its strength. As a result, the outward wave stalls within a few hundred kilometers of the core. This stalling poses a central challenge to the explosion mechanism. If the shock cannot be revived, the collapse continues, and the star may form a black hole directly without a visible supernova. For decades, astrophysicists debated how the shock could overcome these obstacles. The solution that emerged is the neutrino heating mechanism. Neutrinos produced in vast numbers during electron capture and other nuclear reactions stream outward from the proto-neutron star. Though the majority escape into space a fraction, are absorbed in the region just behind the stalled shock. The absorption deposits energy into the matter, heating it and creating pressure that helps push the shock outward again. This process is not instantaneous. The neutrino heating must act for several seconds to accumulate enough energy. During this time, the matter between the proto-neutron star and the shock undergoes turbulent convection. Heated material rises while cooler matter sinks, stirring the region and allowing the deposited energy to spread more evenly. Multidimensional instabilities amplify this effect, with sloshing and spiral motions redistributing heat and helping maintain the shock. Eventually, the combined action of neutrino heating and turbulent mixing revives the shock, allowing it to continue outward through the star. The collapse of the core also produces a torrent of neutrinos that escape into space. These neutrinos are the first messengers of the event, arriving at distant detectors before any light escapes from the star. The supernova of 1987 provided direct confirmation of this process, when detectors on Earth recorded a brief burst of neutrinos hours before the visible explosion was observed. This detection remains one of the most significant pieces of evidence for the theoretical framework of core collapse. It confirmed that neutrinos indeed carry away the majority of the gravitational energy released during the implosion. Once the shock is revived and begins its outward journey, it sets in motion the transformation of the star. The shock heats and compresses the overlying shells, halting their infall and launching them outward. The velocity of the ejected material reaches thousands of kilometers per second. As the shock moves through the outer layers, it triggers additional nuclear reactions. In these conditions, with abundant free neutrons available, rapid neutron capture takes place. Known as the R process, this pathway produces many of the heaviest elements in the universe. Gold, platinum, and other rare elements are synthesized in seconds during this explosive phase. The core, now a proto-neutron star, continues to emit neutrinos for tens of seconds as it cools and stabilizes. If the mass of the core remains below the maximum limit for neutron star stability, it will settle into a permanent neutron star, a dense remnant only about 20 kilometers across, but with more mass than the Sun. If, however, the core accretes too much fallback material, or if the progenitor star was especially massive, the neutron star may collapse further into a black hole. The distinction between these outcomes depends on the delicate balance of mass and the strength of the explosion. From the outside, these interior processes remain invisible until the shock reaches the stellar surface. At that moment, a phenomenon called shock breakout occurs. The star brightens suddenly as photons escape for the first time since collapse began. This flash marks the visible beginning of the supernova. Over the following days and weeks, the expelled material continues to expand and cool, producing the characteristic light curve that astronomers observe. The brightness and shape of this light curve carry information about the amount of material ejected, the energy of the explosion, and the elements synthesized within. The dynamics of core collapse also leave behind distinct signatures in the debris. Supernova remnants observed with telescopes show structures shaped by the turbulence and instabilities that occurred during shock revival. Clumps of heavy elements, asymmetric outflows, and large-scale mixing all point to the chaotic conditions in the collapsing star. Observations across the electromagnetic spectrum from radio waves to X-rays reveal the distribution of elements and the velocities of the ejector, providing a detailed record of the processes that occurred during collapse and explosion. Gravitational waves may also accompany core collapse. Asymmetric motions during the implosion and rebound create ripples in space-time that propagate outward. These signals are faint compared to those produced by merging neutron stars or black holes, but they are an expected consequence of the violent motions in the collapsing core. Detecting them would provide a new way to probe the dynamics of supernovae complementing neutrino and electromagnetic observations. Current gravitational wave observatories are approaching the sensitivity needed to detect such events within our galaxy, promising a more complete view of stellar death in the future. In summary, the core collapse process unfolds in rapid succession. The iron core exceeds the Chandrasekhar limit. Electron degeneracy pressure fails the core, implodes neutron degeneracy, halts the collapse. A shock wave forms and stalls. Neutrino heating revives the shock, and the explosion expels the outer layers while leaving behind a compact remnant. Each stage is governed by well-understood physics, confirmed by laboratory experiments, simulations, and astronomical observations. The details of turbulence, convection, and neutrino transport remain active areas of research, but the broad picture is secure. Massive stars die not in silence, but in collapse and explosion, reshaping their surroundings and enriching the galaxy with heavy elements. At this stage in the narrative, the star's transformation from a stable luminous body to a collapsing core and outward blasting supernova is nearly complete. The interplay of gravity, nuclear physics, and particle processes has determined its fate. The result is both destructive and creative. The star is gone, but its elements are dispersed into space, carrying the seeds of future stars, planets, and life. The revival of the shock wave inside a collapsing star marks the transition from inward implosion to outward explosion. Once the shock is re-energized, it begins to travel steadily outward through the concentric shells that had built up during the star's life. Each shell, whether composed of silicon, oxygen, neon carbon, helium, or hydrogen, responds differently to the advancing front. The passage of the shock compresses and heats the material, halting its inward collapse and launching it outward at high velocity. In the process, new nuclear reactions are ignited. For a brief moment, matter is subjected to temperatures and pressures so high that nuclei are rearranged into heavier forms. The result is nucleosynthesis under explosive conditions, which differs from the slow fusion that sustained the star in earlier stages. As the shock continues outward, the dense matter behind it expands and cools. In this hot environment, free neutrons are abundant, released from nuclei by the intense heat and photodisintegration processes. These neutrons can be rapidly captured by atomic nuclei before the nuclei have time to undergo radioactive decay. This pathway, known as the rapid neutron capture process, or R process, produces some of the heaviest elements in the universe. Gold, platinum, and uranium are among the products of this chain of reactions. These elements do not form during ordinary stellar fusion, because the conditions of temperature, density, and neutron flux are never sufficient. Only in the extraordinary environment of a supernova or a similar cataclysm can they be assembled. The formation of such elements is supported by observations of supernova remnants and by the chemical composition of ancient stars. Astronomers studying old stars in the halo of the Milky Way find patterns of heavy element abundances that are consistent with the R process. These stars formed early in the galaxy's history, shortly after the first generations of massive stars exploded. Their chemical fingerprints preserve the evidence that supernova seeded the young galaxy with heavy elements. This provides strong confirmation that core collapse supernovae play a central role in the chemical enrichment of the universe. The light curve of a supernova also reflects the products of these reactions. After the initial shock breakout, the brightness of the explosion is sustained by the radioactive decay of unstable isotopes produced in the blast. Nickel-56, created in significant amounts, decays into cobalt-56 and then into iron-56, releasing gamma rays that heat the expanding ejector. The reprocessing of this energy into visible light produces the characteristic plateau or decline phases seen in supernova light curves. Thus, the brightness observed across weeks and months carries information about the nucleosynthesis that occurred in the first moments of the explosion. The journey of the shock through the star is not smooth or symmetrical. Multidimensional instabilities and turbulence that arose during shock revival continue to shape the explosion. The ejector may be clumpy, with some regions enriched in heavy elements, while others contain mostly lighter material. These asymmetries are visible in supernova remnants observed today. The Crab Nebula Cassiopeia A and other remnants show knots filaments and uneven distributions of material. These structures record the chaotic flows that occurred deep within the star during its collapse and explosion. The speed of the expanding ejector varies with mass and composition. The lighter outer layers, such as hydrogen and helium, are accelerated to higher velocities, sometimes exceeding 10,000 kilometers per second. The heavier inner layers move more slowly but carry the freshly synthesized elements. Over time, the different layers mix, spreading elements throughout the remnant. Eventually, these materials enrich the surrounding interstellar medium, where they may become part of new generations of stars and planets. In this way, the death of a massive star is directly linked to the cycle of cosmic renewal. Neutrinos continue to play a role during these first seconds to minutes of the explosion. As they stream outward from the cooling proto-neutron star, they influence the composition of the surrounding matter. The balance between protons and neutrons in the ejector is partly controlled by neutrino interactions. This balance affects which isotopes are produced during nucleosynthesis. A neutron-rich environment favors the R process, while a proton-rich environment allows different nuclear pathways. The outcome depends sensitively on the spectrum and intensity of the neutrino flux, tying the chemistry of the explosion to the physics of the dense core. In some models, additional processes such as magnetic fields and rotation influence the dynamics of the explosion. Strong magnetic fields may channel matter into jets, focusing the outflow along specific directions. If the star rotates rapidly, the collapse and explosion can produce anisotropic structures that further shape the distribution of ejecta. In certain extreme cases, these conditions may give rise to particularly energetic events, such as hypernovae or long-duration gamma-ray bursts. Although such scenarios are rare, they illustrate the variety of outcomes that can result from the basic mechanism of core collapse. The shock wave continues to expand until it reaches the outermost layers of the star. If the progenitor star retained its hydrogen envelope, the breakout produces a distinct light curve with a long plateau phase, as seen in Type 2P supernovae. If the hydrogen had been lost through stellar winds or binary interaction, the explosion appears as a different class, such as Type Ib or Ek. In all cases, however, the origin of the explosion lies in the same chain of events: core collapse, shock formation, neutrino heating, and the outward journey of the shock through the star. By the time the shock emerges into space, the star has been utterly transformed. The luminous surface that once radiated steadily is gone, replaced by an expanding cloud of debris. The central core has contracted to a neutron star, or in some cases a black hole. The layers that once burned hydrogen, helium, and heavier elements have been disrupted and cast outward. The material that once formed a coherent stellar structure is now a diffuse and chaotic mixture spreading into interstellar space. For astronomers, the outward expansion provides the first direct evidence of what happened inside. Light curves, spectra, and eventually supernova remnants reveal the sequence of processes that unfolded in seconds within the collapsing core. Each observation adds detail to the picture, confirming the models of nucleosynthesis, neutrino heating, and shock dynamics. Though the core itself remains hidden from direct view, the expelled material and its chemical makeup provide a record of the star's final moments. In this way, the shock that begins as a stalled wave near the proto-neutron star becomes the instrument through which a star's death reshapes its environment. Its outward march distributes energy and heavy elements, drives turbulence into the interstellar medium, and seeds the cosmos with the raw materials for new stars and planets. The process is violent in physical terms, but when described step by step, it is a natural progression governed by well-established laws of physics. Gravity initiates the collapse, quantum forces halt, the core neutrinos revive the shock, and the explosion disperses the elements. Together, these stages form the complete cycle of stellar death and renewal. At this point in the narrative, the star is no longer a coherent body but an expanding remnant. The outer layers continue their flight into space, the inner core contracts into stability or collapse, and the light from radioactive decay illuminates the debris. The outcome is visible across the cosmos as a supernova, but the story of the event lies in the processes that occurred deep within, hidden from view, yet central to the life and death of stars. The outward moving blast of a core collapse supernova is one of the most luminous events in the universe, yet the light visible to observers is only the surface expression of processes that began deep inside. Once the shock breaks free of the stellar surface, the supernova becomes visible across vast distances. The light curve, which is the graph of brightness over time, provides a key record of the physics at work. The brightness rises quickly, often within hours to days of the shock breakout, as the outer layers of the star are heated and radiate energy. The details of the rise depend on the structure of the progenitor star. A red supergiant with a large radius produces a slower, broader rise, while a more compact star such as a blue supergiant or a stripped envelope star produces a sharper peak. After the initial peak, the light curve typically shows a plateau or a decline phase. In Type 2p supernovae, which retain their hydrogen envelopes, the plateau is sustained for weeks, as the expanding hydrogen recombines and radiates energy. In other types, such as Ib and Eek, where hydrogen and sometimes helium are absent, the light declines more quickly because the available material to radiate is smaller. In all cases, the continued brightness is powered by radioactive isotopes created during the explosion. Nickel-56 is the most important. It is produced in large amounts in the innermost ejecta, and its decay chain to cobalt-56 and then iron-56 releases gamma rays. These gamma rays deposit energy in the ejecta, heating it and sustaining the light output long after the initial shock energy has dissipated. The spectra of supernovae, which show the distribution of light at different wavelengths, reveal the composition and velocity of the ejecta. Hydrogen lines dominate in Type 2 supernovae, while helium and heavier element lines mark Type Ib and Ik. Broad absorption features indicate the rapid expansion of the material, with velocities measured in thousands of kilometers per second. Over time, the spectra change as the outer layers become transparent and deeper layers are revealed. This evolution allows astronomers to map the structure of the exploding star from the outside inward, reconstructing the sequence of layers that once burned different fuels. In addition to light, supernovae release vast amounts of kinetic energy. The ejected mass, often several times that of the Sun, is accelerated to high velocities, imparting energies on the order of 10 to the power of 44 joules. This energy drives the expansion of the supernova remnant, a shell of gas and dust that continues to grow for thousands of years. Observed remnants such as the Crab Nebula or Cassiopeia show the aftermath of such explosions, with filaments, knots and expanding shells visible across multiple wavelengths. These remnants are not just visual displays, they are laboratories for understanding the processes of shock heating nucleosynthesis and the interaction of stellar debris with the interstellar medium. The shape of the explosion is rarely perfectly spherical. Observations of remnants reveal asymmetries, suggesting that the explosion mechanism itself produces uneven flows. Turbulence during shock revival convection in the gain region and instabilities in the expanding shock all contribute to this asymmetry. In some cases, jets or bipolar outflows are observed, indicating that rotation and magnetic fields may have played roles in shaping the blast. These variations add complexity to the picture, but they also provide valuable clues. The non-uniform distribution of elements in remnants helps confirm models that include multidimensional effects rather than assuming perfect symmetry. Supernovae are also important sources of gravitational waves, though detecting them is difficult. The rapid asymmetric motions of matter in the core produce ripples in space-time, but these signals are faint compared to those from merging neutron stars or black holes. Nevertheless, they remain a target for gravitational wave observatories. Detecting such waves from a nearby supernova would provide a direct probe of the inner dynamics of core collapse, complementing neutrino and electromagnetic observations. Together, these three messengers, light neutrinos and gravitational waves, form the foundation of multi-messenger astronomy, which aims to study cosmic events from multiple perspectives at once. The chemical enrichment of the galaxy is one of the most enduring consequences of supernovae. The heavy elements created during nucleosynthesis are dispersed into the interstellar medium by the explosion. Over time, this enriched gas mixes with existing material, altering the chemical composition of the galaxy. Subsequent generations of stars form from this enriched material, inheriting elements such as carbon, oxygen, silicon, and iron. Planets and ultimately life depend on these heavy elements. In this way, supernovae are both the death of stars and the source of the materials required for new stars and planetary systems to arise. Evidence for this enrichment is found in meteorites in our own solar system. Some isotopes present in meteorites are the decay products of short-lived radioactive nuclei that could only have been produced in a nearby supernova shortly before the formation of the solar system. This indicates that the Sun and planets were born in a region already influenced by the death of massive stars. The fingerprints of past supernovae are therefore recorded not only in distant galaxies, but in the rocks beneath our feet. Different types of core collapse supernovae arise depending on the progenitor star's structure. A star that retains its hydrogen envelope becomes a Type II supernova, with characteristic hydrogen lines in its spectrum. A star that loses hydrogen but retains helium produces a Type Ib supernova, while a star stripped of both hydrogen and helium produces a Type Ek. These differences are shaped by mass loss, through stellar winds or binary interactions before collapse. Despite these surface variations, the underlying mechanism of core collapse, shock, revival, and explosion remains the same. The brightness and frequency of supernovae make them valuable tools for studying the universe. They serve as markers for tracing star formation rates, galactic evolution, and the distribution of elements. Their remnants provide insight into particle acceleration, as shocks in expanding shells accelerate cosmic rays that later reach Earth. The study of supernovae therefore connects multiple areas of astrophysics, from nuclear physics and particle interactions to galaxy formation and cosmic ray propagation. From the perspective of the collapsing star itself, however, the sequence is straightforward. The core collapses, the shock forms and is revived, the ejecta are expelled, and the remnant is left behind. The light neutrinos and gravitational waves observed at great distances are simply the echoes of this chain of events. What was once a stable star burning its fuel layer by layer has now been transformed into an expanding shell and a dense remnant. The outward motion of the shock is the final expression of the forces that govern the star's life and death. At this stage of the story, the explosion has become fully visible. The supernova shines brightly, its spectra reveal its composition, and its ejecta race outward into space. Yet the true driver of the event remains hidden: the collapse of the core and the neutrino-driven revival of the shock. Observers see the after effects, but the decisive processes occurred in silence deep inside the star, in the moments when gravity overwhelmed every other force. While core collapse supernovae arise from the deaths of massive stars, there exists another distinct path to stellar destruction: the thermonuclear explosion of a white dwarf. This event, known as a Type Ia supernova, does not require a massive progenitor, but instead occurs when a smaller star is pushed beyond its limits by external circumstances. A white dwarf is the remnant left behind when a star of moderate mass like the Sun exhausts its fuel and sheds its outer layers. Supported by electron degeneracy pressure, the white dwarf is stable so long as its mass remains below the Chandrasekhar limit of about 1.5 times the mass of the Sun. If it approaches or exceeds that limit, the balance collapses not by gravitational implosion into a neutron star, but by runaway nuclear fusion that consumes the star in its entirety. The most common way this limit is reached is through mass transfer in a binary system. A white dwarf may orbit a larger companion, such as a red giant. As the companion evolves and expands, gas from its outer layers spills onto the white dwarf, forming an accretion disk and steadily increasing its mass. With each increment of mass, the density and temperature of the white dwarf's core rise. Because degeneracy pressure does not depend on temperature, the white dwarf does not expand in response to the heating. Instead, conditions become ideal for an uncontrolled chain reaction. Once carbon fusion ignites in the dense core, the reaction cannot be regulated as it is in normal stars. The result is a thermonuclear runaway that burns through the entire white dwarf in seconds. Another possible route is the merger of two white dwarfs in a binary system. Over time, gravitational radiation causes the orbit of the pair to shrink, eventually bringing them together. When they collide, their combined mass exceeds the Chandrasekhar limit, and conditions trigger the same runaway fusion. In both pathways, the outcome is the same. The white dwarf is obliterated in a catastrophic release of energy, leaving no remnant behind. The mechanism of a Type Ia explosion differs from core collapse in fundamental ways. Instead of gravity crushing matter to neutron densities, it is the inability of degeneracy pressure to regulate temperature that drives the process. Once carbon fusion begins, the temperature rises, which increases the fusion rate, which further raises the temperature, creating a runaway reaction. Normal stars avoid this instability because their pressure depends on temperature. When fusion rates increase, the star expands and cools, restoring balance. In a degenerate, star pressure is independent of temperature, so no expansion occurs until it is far too late. The result is a detonation that unbinds the entire star. The energy released in a Type Ia supernova is comparable to that of a core collapse event, but the composition of the ejector differs. The runaway fusion burns much of the carbon and oxygen into intermediate mass elements, such as silicon, sulfur, and calcium, and produces large amounts of nickel-56. The decay of nickel to cobalt and then to iron powers the light curve, which has a distinctive shape. Type Ia supernovae lack hydrogen lines in their spectra, because the progenitor is a white dwarf, not a massive hydrogen-rich star. Instead, their spectra are dominated by silicon features near maximum brightness. The uniformity of Type Ia explosions makes them valuable cosmic tools. Because they arise from white dwarfs reaching nearly the same critical mass, their peak luminosities are relatively consistent. After corrections based on light curve shapes, Type Ia supernovae serve as standard candles for measuring cosmic distances. Observations of these explosions in distant galaxies reveal that the expansion of the universe is accelerating a discovery that led to the concept of dark energy. Thus, the death of small stars in binary systems has provided key insights into the larger scales of the cosmos. Despite their usefulness, the precise details of how Type Ia supernovae ignite remain under study. The nature of the binary companion, the rate of accretion, and the conditions leading to detonation are all areas of active research. Some models suggest a deflagration where burning spreads subsonically transitions into a detonation, while others propose detonation begins directly. Observations of unusual supernovae that do not fit neatly into the standard pattern suggest that multiple pathways may exist, including sub-Chandrasekhar explosions triggered by helium shells on the white dwarf surface. The importance of Type Ia supernovae extends to galactic chemistry. They are major producers of iron and iron group elements, which they release into the interstellar medium in great quantities, while core collapse supernovae produce a wide range of elements up to iron and beyond through rapid neutron capture. Type Ia events dominate the production of iron itself. This division of labor is reflected in the chemical evolution of galaxies. By comparing the ratios of different elements in stars of varying ages, astronomers trace the contributions of both core collapse and thermonuclear supernovae to galactic enrichment. Observationally, Type Ia supernovae are identified by their light curves and spectra. Their peak brightnesses are similar, but small variations correlate with the width of the light curve. Brighter supernovae fade more slowly. This empirical relationship, known as the Phillips relation, is what allows astronomers to calibrate them as standard candles. The absence of hydrogen and the presence of silicon absorption features provide additional classification. Surveys that search for supernovae routinely identify Type Ia events across a wide range of distances, making them essential tools for mapping the universe. The theoretical framework for Type Ia supernovae highlights the universality of physical laws. The same Chandrasekhar limit that governs the collapse of massive stars also sets the boundary for white dwarfs. In one case, exceeding the limit leads to gravitational collapse into a neutron star or black hole. In the other, it triggers runaway fusion that unbinds the star completely. Both outcomes illustrate how quantum mechanical effects acting at the level of electrons in dense matter determine the destinies of stars and the enrichment of galaxies. From the standpoint of the larger story of stellar collapse, Type Ia supernovae represent a parallel path. They are not born of massive stars exhausting their cores, but of small stars pushed to instability by mass gain. Their explosions are not the rebound of collapsing matter, but the unregulated ignition of fusion. Yet their consequences are equally profound: the complete destruction of the progenitor, the dispersal of heavy elements, and the illumination of galaxies. The two types of supernovae together ensure that the universe is enriched with both iron group elements and the heavier nuclei forged in collapse-driven explosions. At this point in the narrative, the contrast between core collapse and thermonuclear explosions has become clear. Both follow from the same physical principles of quantum mechanics, nuclear fusion, and gravity, but they manifest in different environments. In massive stars, gravity drives collapse until nuclear forces intervene. In white dwarfs, degeneracy pressure resists collapse until excess mass triggers a thermonuclear runaway. The outcomes differ, yet both are final steps in the lives of stars and both play indispensable roles in shaping the cosmos. While most supernovae are explained by either core collapse in massive stars or thermonuclear runaway in white dwarfs, there exists another path that is rarer and even more extreme: the pair instability supernova. This outcome occurs only in very massive stars, those born with initial masses well above 100 times the mass of the Sun. In such stars, the interior temperatures during late burning stages become so high that photons in the core possess enough energy to create particle-antiparticle pairs of electrons and positrons. This process removes pressure from the core, because the energy that once contributed to supporting it as radiation pressure is now locked into the rest mass of the pairs. With radiation pressure reduced, the balance between gravity and outward force is disturbed, and collapse begins in a different way than in ordinary core collapse events. The formation of electron-positron pairs is central to this instability. In most stars, photons contribute to pressure simply by their existence, as high-energy particles bouncing among nuclei and electrons. At sufficiently high temperatures, however, a photon can spontaneously transform into an electron and a positron. These pairs quickly annihilate back into photons, but the constant creation and destruction of pairs drains energy from the radiation field and lowers the effective pressure. Gravity responds by compressing the star further, which in turn raises temperatures, producing more pairs. The cycle accelerates and instability grows. The outcome depends strongly on the total mass of the star. For stars on the lower end of the very massive range, pair production induces partial collapse of the core. The collapse raises temperatures high enough to ignite explosive oxygen and silicon burning. The sudden release of nuclear energy can reverse the collapse and completely disrupt the star in a thermonuclear explosion. Unlike ordinary core collapse supernovae, this explosion leaves no compact remnant behind. The star is obliterated entirely, dispersing its material into space. Such explosions are called pair instability supernovae. For stars of intermediate mass in this regime, the result may be pulsational pair instability. In this scenario, pair production triggers repeated partial collapses followed by explosive burning. Each pulse expels part of the star's outer layers, while the core remains intact for a time. After several such cycles, the remaining core may collapse in a conventional core collapse supernova, or if it grows too massive, directly into a black hole. Pulsational pair instability events are thought to produce unusual transients observed in the universe, marked by multiple outbursts before the final explosion. For stars at the very upper end of the mass range, even explosive burning cannot reverse collapse. The star's gravity is so intense that once pair production reduces pressure, collapse proceeds inexorably into a black hole. In these cases, little or no light is emitted, and the event may be nearly invisible except through gravitational waves or neutrinos. The precise boundaries between these outcomes are determined by stellar mass metallicity and rotation, all of which affect how the star evolves during its lifetime. Pair instability supernovae differ observationally from other types. Because they disrupt the star completely, they eject enormous amounts of material, including several solar masses of nickel-56. The radioactive decay of this nickel produces an exceptionally bright and long-lasting light curve. Observations of certain unusually luminous supernovae in distant galaxies have been interpreted as possible pair instability events. These explosions shine much more brightly and persist longer than ordinary supernovae, consistent with the large quantities of radioactive material predicted by models. The physics of pair production is well established from quantum electrodynamics. Laboratory experiments confirm that photons of sufficiently high energy can create electron-positron pairs. In stars, the relevant temperatures exceed billions of degrees, conditions reached only in the cores of the most massive stars. The inclusion of pair production in stellar models naturally leads to instabilities once the star surpasses a critical mass. These models reproduce the expected behaviors of full disruption, pulsational mass loss or collapse to a black hole depending on initial conditions. Pair instability supernovae are thought to have been more common in the early universe, when the first generations of stars were far more massive on average than stars formed today. With few heavy elements to cool the gas, primordial clouds produce stars of hundreds of solar masses. Many of these may have ended their lives through pair instability explosions, contributing to the chemical enrichment of the early cosmos. Today, such massive stars are rare, but they may still form under special conditions. Observations of distant luminous supernovae may provide glimpses of this ancient mode of stellar death. The nuclear synthesis in pair instability supernovae is distinctive. The complete disruption of the star produces large quantities of intermediate mass elements such as oxygen, silicon, and sulfur, along with iron group elements from explosive burning. Because no compact remnant remains, all of the products are dispersed into the interstellar medium. This contrasts with core collapse supernovae, where part of the star falls back onto a neutron star or black hole. The chemical signatures of ancient stars that contain unusual element ratios may reflect the influence of pair instability explosions in the early universe. From the perspective of stellar physics, the pair instability pathway underscores how different physical processes can govern stellar death. Core collapse is triggered by the inability of iron to release energy through fusion, while thermonuclear runaway in white dwarfs arises from uncontrolled carbon ignition under degeneracy conditions. Pair instability, by contrast, originates from the conversion of photons into particle-antiparticle pairs, reducing radiation pressure. Each mechanism is distinct, yet all are consequences of the same fundamental laws applied in extreme regimes. The study of pair instability events also highlights the connection between microphysics and cosmic phenomena. A single quantum process, photon conversion, into an electron and a positron determines whether a star of hundreds of solar masses lives or dies, quietly collapses into a black hole, or ends in a titanic explosion. The fate of such a massive star depends on a subtle interplay between quantum electrodynamics, nuclear burning, and gravitational dynamics. This illustrates the profound reach of fundamental physics across scales from particles to galaxies. In the broader context of stellar collapse, pair instability explosions occupy a rare but significant niche. They demonstrate that not all stellar deaths follow the same pattern. While most stars die as white dwarfs, neutron stars or black holes, a select few undergo complete destruction, leaving nothing behind but expanding debris and chemical signatures. These events remind us that stellar evolution has multiple endpoints, each determined by the delicate balance of mass, pressure, temperature, and the physics of particles. At this stage of the narrative, the catalogue of stellar death mechanisms now includes the pair instability pathway, alongside core collapse and thermonuclear runaway. Together, these processes account for the observed diversity of supernovae and their contributions to the chemical evolution of the universe. They reveal the wide range of outcomes possible when stars exhaust their fuel, and they highlight the different roles of quantum mechanics, nuclear physics, and gravity in shaping the cosmos. When a supernova has completed its outward blast and the ejecta are on their way into interstellar space, what remains at the center is a compact remnant. The nature of this remnant depends on the original mass of the progenitor star and the dynamics of the explosion. The three principal outcomes are white dwarfs, neutron stars, and black holes. Each represents a different balance between gravity and the quantum mechanical pressures that resist further collapse. A white dwarf is the simplest outcome, though it arises not from massive stars that undergo core collapse, but from stars with initial masses less than about 8 times that of the Sun. Such stars never build iron cores, so they avoid catastrophic collapse. Instead, they shed their outer layers in planetary nebulae and leave behind a carbon-oxygen core. Supported by electron degeneracy pressure, the white dwarf remains stable, so long as its mass is below the Chandrasekhar limit. These remnants are roughly the size of Earth, but contain half the mass of the Sun or more, making them incredibly dense. Over billions of years, they cool and fade, becoming faint embers of their former stars. In the case of massive stars, collapse produces either a neutron star or a black hole. If the collapsing core is less than about 2 to 3 times, the mass of the Sun, neutron degeneracy pressure, and nuclear forces can halt further collapse. The result is a neutron star, a compact object about 20 kilometers across, with a mass greater than the Sun. Neutron stars are so dense that a teaspoon of their matter would weigh billions of tons. Their surfaces have gravity 200 billion times stronger than Earth's, and their magnetic fields can be trillions of times stronger than the Sun's. Despite their exotic nature, they are stable endpoints supported by the same exclusion principle that holds up white dwarfs only applied to neutrons instead of electrons. Some neutron stars are observed as pulsars, beacons of radio, and other electromagnetic waves that sweep across space as the star rotates. The rapid rotation and strong magnetic fields generate radiation beams that, when aligned with Earth, produce periodic pulses. Others may be seen as magnetars neutron stars with magnetic fields so intense that they can power bursts of X-rays and gamma rays. These observable properties provide evidence of the extraordinary conditions inside neutron stars, conditions that cannot be replicated in laboratories, but can be inferred through astronomical study. If the collapsing core is more massive than about 3 solar masses, not even neutron degeneracy pressure can resist gravity. In that case, the collapse continues inexorably until a black hole forms. A black hole is defined by the presence of an event horizon, a boundary beyond which not even light can escape. Within this horizon, the known laws of physics cannot describe matter in detail. General relativity predicts that the core contracts to a singularity, a point of infinite density, though many physicists expect that a more complete theory of quantum gravity will eventually provide a more accurate description. Regardless of the details, the black hole remains hidden from direct view, its presence inferred only through its gravitational effects on surrounding matter. The distinction between neutron star and black hole formation is not always sharp. In some cases, the explosion may initially produce a neutron star, but fallback of ejected material can add mass and push it over the stability limit, leading to delayed collapse into a black hole. The threshold depends on the equation of state of dense matter, which describes how pressure responds to density in conditions far beyond those accessible on Earth. Determining this equation of state is one of the central challenges in nuclear astrophysics. Observations of neutron star masses, radii, and gravitational wave signals from mergers provide constraints, but uncertainties remain. White dwarfs, neutron stars, and black holes each represent the victory of different forces over gravity. In white dwarfs, electron degeneracy pressure is sufficient. In neutron stars, neutron degeneracy and nuclear forces succeed. In black holes, no known force can prevent collapse. These outcomes demonstrate how the same fundamental principles apply across a wide spectrum of scales. The exclusion principle of quantum mechanics, formulated to describe the behavior of electrons in atoms, dictates the fate of stars millions of times larger than Earth. The environments surrounding compact remnants are often active and dynamic. Neutron stars can accrete material from binary companions, producing powerful X-ray emissions as the matter falls onto the dense surface. Black holes can do the same, forming accretion disks that shine brightly in X-rays as gas spirals inward. In some systems, jets of material are launched at nearly the speed of light, powered by the rotational energy of the black hole or neutron star. These phenomena show that the end of a star's life does not always mean quiet isolation. In binaries, remnants can remain among the most energetic objects in the universe. Observations confirm the diversity of compact remnants. White dwarfs are detected by their faint light in the Milky Way and in globular clusters. Neutron stars are known through pulsars, X-ray binaries, and magnetars. Black holes are inferred from binary systems where unseen companions exert gravitational influence, or from gravitational waves generated when two black holes merge. Each detection adds evidence to the framework that stellar collapse leads to these endpoints. The agreement between theory and observation is strong, even as many details remain subjects of research. The existence of compact remnants also links stellar death to broader cosmic processes. Neutron stars merging in binary systems have been shown to produce gravitational waves and electromagnetic counterparts, as confirmed in the event observed in 2017. That same event also revealed heavy element nucleosynthesis, further connecting stellar collapse to the origin of matter. Black holes, though silent, influence galactic evolution through the energy released by accretion. White dwarfs, though faint, contribute to the history of galactic chemistry when they explode as Type Ia supernovae. In the cycle of stellar evolution, compact remnants mark both an end and a beginning. The star itself is gone, its structure dissolved by collapse or explosion. What remains is either a cooling ember, a neutron-rich sphere, or an invisible horizon. Yet the consequences of their formation continue. They enrich galaxies, they generate observable signals across the electromagnetic spectrum, they emit gravitational waves, and they challenge physicists to extend understanding of matter under the most extreme conditions. At this stage in the description, the narrative of stellar collapse has reached the remnants that remain after the explosive phase. These objects are not only endpoints but also laboratories of physics, where gravity, quantum mechanics, and nuclear forces meet in ways that cannot be reproduced elsewhere. Each remnant is a quiet but enduring record of the processes that unfolded during collapse, a final state that embodies the balance or failure of the fundamental forces of nature. When the blast wave of a supernova carries the outer layers of a star into space, It also carries the record of nuclear transformations that occurred both during the star's lifetime and in its final collapse. These transformations are referred to as nucleosynthesis, the building of new atomic nuclei from protons and neutrons. Throughout its life, a star steadily fuses lighter elements into heavier ones, beginning with hydrogen into helium, then helium into carbon and oxygen, then progressively up the chain toward iron. Each of these stages provides the energy that sustains the star. But in the explosion, conditions arise that are far more extreme than in steady burning, and these conditions allow the creation of nuclei that could never form otherwise. One of the principal processes during a supernova is explosive nucleosynthesis. When the shock wave passes through the layers of silicon and oxygen, the sudden increase in temperature drives rapid fusion reactions. Silicon burning in particular proceeds at a pace far faster than in the quiescent star, producing large amounts of iron group elements in seconds. The abundance of nickel-56, which later decays to iron-56, is a direct result of this process. The decay chain not only shapes the chemical composition of the ejector, but also powers the visible light curve of the supernova, as the gamma rays from decay are reprocessed into optical light. In addition to explosive fusion, the supernova environment enables the rapid neutron capture process, or R process. This occurs when nuclei are bombarded by a high flux of free neutrons. Under such conditions, a nucleus can capture several neutrons before it has a chance to undergo beta decay. This rapid sequence of captures allows the formation of nuclei much heavier than iron, climbing far up the periodic table into the realms of gold, platinum, thorium, and uranium. The R process requires both abundant neutrons and extremely high densities and temperatures conditions that appear naturally in the zone surrounding the protoneutron star and in the expanding ejector energized by neutrinos. Evidence for the R process is found in both the chemical composition of old stars and in the distribution of elements in the solar system. Observations of ancient halo stars reveal heavy element ratios that match predictions of R process nucleosynthesis. These stars must have formed from gas enriched by one or a few early supernovae, preserving the chemical fingerprints of those explosions. In meteorites and terrestrial rocks, the presence of R process isotopes provides additional confirmation that such processes contributed to the material that formed the solar system. Together, these clues indicate that supernovae are among the primary sources of the heaviest elements in the universe. The nucleosynthesis in supernovae is not uniform. Different zones produce different elements depending on their temperature, density, and neutron richness. Close to the core, where conditions are most extreme, heavy R process elements are formed. Further out, explosive oxygen and silicon burning produce intermediate mass elements, such as sulfur, argon, and calcium. Still further out, the shock wave may only heat the material enough to redistribute lighter elements without forging new ones. The result is a layered ejector with distinct chemical signatures, though turbulence and mixing often blur the boundaries. Not all heavy elements may come from ordinary core collapse supernovae. Observations suggest that neutron star mergers also contribute to R process enrichment, perhaps even dominating it in some galaxies. However, core collapse supernovae remain an essential source of elements up to iron, and likely contribute significantly to the production of heavier nuclei as well. The precise balance between these sources is still a topic of research, but the central role of collapse-driven explosions in galactic chemical evolution is undisputed. Supernova nucleosynthesis also explains the abundance of many stable isotopes. For example, elements like magnesium and silicon are produced in large amounts during hydrostatic burning stages and then released during the explosion. Iron and nickel isotopes are forged in the final silicon burning and explosive phases. The diversity of isotopes found in nature reflects the complex interplay of burning stages and explosive processes. Each isotope serves as a marker of the physical conditions under which it was created. The role of neutrinos in nucleosynthesis should not be overlooked. The so-called neutrino-driven wind, an outflow of matter from the surface of the proto-neutron star, provides an environment where additional nucleosynthesis can occur. Depending on whether the wind is neutron-rich or proton-rich, different nuclear pathways may dominate. A neutron-rich wind favors R-process synthesis, while a proton-rich wind may enable the production of certain rare isotopes through rapid proton capture. The details depend sensitively on neutrino interactions, illustrating again how these elusive particles influence the chemical outcomes of stellar death. Observational evidence of nucleosynthesis comes from spectra of supernovae and their remnants. Emission lines of elements such as oxygen, calcium, and iron reveal the composition of the ejecta. In some cases, gamma rays from the decay of radioactive isotopes like cobalt-56 have been directly detected, providing direct confirmation of explosive nucleosynthesis. Supernova remnants observed in X-rays show distributions of heavy elements that match theoretical predictions, reinforcing the link between models and real explosions. The significance of nucleosynthesis extends beyond astrophysics. The elements produced in stars and supernovae form the foundation of planets and life. Carbon, nitrogen, and oxygen are essential components of organic molecules. Iron is the core of Earth and the basis of hemoglobin in blood. Calcium strengthens bones, and trace elements like copper and zinc play roles in biological systems. All of these elements originated in the nuclear furnaces of stars and in the violent crucibles of supernovae. Without these processes, the universe would be composed primarily of hydrogen and helium with little complexity. In the larger picture of galactic evolution, nucleosynthesis in supernovae ensures that each generation of stars forms from material more enriched than the last. The earliest stars contained only hydrogen and helium, but their death seeded the cosmos with heavier elements. Later generations incorporated these elements, enabling the formation of rocky planets and eventually life. Thus, the cycle of stellar birth and death is also the story of the chemical transformation of the universe. At this stage of the description, the focus rests on how collapse-driven explosions act not only as endings but as origins. They destroy the progenitor star, yet they create the elements that make complex matter possible. The processes of explosive burning rapid neutron capture and neutrino-driven nucleosynthesis together explain the diversity of elements observed. In this way, the quiet fusion that sustained stars for millions of years finds its ultimate counterpart in the sudden violent nucleosynthesis of stellar death. The death of a star through collapse and explosion does not pass quietly. Even after the blast has unfolded, the universe continues to carry its signatures in forms that astronomers can observe. These signatures include light neutrinos, gravitational waves, and the physical structures left behind as supernova remnants. Together, they provide a comprehensive record of the processes that occurred in the hidden core and the surrounding layers. Each messenger reveals a different piece of the story, and when combined, they allow a coherent reconstruction of the physics of stellar collapse. Light remains the most obvious signal. The brightness of a supernova often rivals or surpasses that of the entire galaxy in which it resides. For weeks or months, it dominates the sky of that region, then gradually fades. The light curve records the initial breakout, the plateau phase for hydrogen-rich explosions, and the long decline powered by radioactive decay. Spectra show the composition and velocity of the ejecta with characteristic features of hydrogen, helium, silicon, oxygen, calcium, and iron. Over time, as the outer layers thin, deeper regions are revealed. The changes in spectral lines allow astronomers to trace the internal structure of the explosion and the elements synthesized within. Neutrinos provide another vital window, though they are far more difficult to detect. In 1987, when a supernova occurred in the Large Magellanic Cloud detectors on Earth, recorded a handful of neutrinos over the course of about 10 seconds. That small sample nevertheless confirmed the prediction that collapse liberates most of its energy in the form of neutrinos. The burst preceded the arrival of visible light as neutrinos escape the core instantly, while photons take hours to diffuse through the outer layers. Future supernovae within our galaxy would produce vastly larger samples with modern detectors, allowing detailed study of neutrino spectra and timing. Such measurements would probe the very conditions of the proto-neutron star and the processes of shock revival. Gravitational waves are a newer messenger predicted by general relativity and confirmed in recent years through the detection of compact object mergers. In a core collapse supernova, asymmetric motions of matter during collapse and rebound are expected to produce faint gravitational wave signals. These ripples in space-time would carry direct information about the internal dynamics of the implosion, unaffected by intervening matter. Detecting them is challenging because the signals are weak compared to those from mergers, but if a supernova occurred within our own galaxy, current observatories might be able to record them. A detection would provide a crucial complement to neutrino and light observations, completing a multi-messenger picture of collapse. The physical remnants of explosions also carry signatures. Expanding shells of gas and dust persist for thousands of years, visible across many wavelengths. In radio waves, they show synchrotron radiation from accelerated electrons. In X-rays, they reveal hot gas heated by the shock. In optical light, they display filaments and knots of glowing material. Examples such as the Crab Nebula or Cassiopeia provide detailed laboratories where the aftermath of supernovae can be studied. By mapping the distribution of elements, astronomers confirm predictions of nucleosynthesis and trace the mixing of layers caused by turbulence. The expansion velocities, shock interactions, and evolving structures tell the ongoing story of how a single stellar death reshapes its surroundings. Compact remnants, whether neutron stars or black holes, are long-term signatures of collapse. Pulsars rotating neutron stars with magnetic beams provide precise timing signals that can be measured over decades. Magnetars emit bursts of high-energy radiation linked to their extreme magnetic fields. Black holes reveal themselves through accretion in binary systems or through the gravitational waves of mergers. Each remnant carries information about the final state of the collapsing core, including its mass composition and stability. In this way, even long after the explosion fades, the remnants continue to testify to the processes of collapse. Uncertainties remain in the details of how collapse leads to explosion. Simulations must account for complex physics across wide scales, nuclear interactions at subatomic levels, neutrino transport through dense matter, hydrodynamic instabilities, and general relativity. The interplay of these factors makes the exact conditions for successful explosions sensitive to small differences. Some models produce robust explosions while others stall. This sensitivity likely reflects real diversity in nature, where some stars explode as visible supernovae while others collapse directly to black holes. The balance between these outcomes and the precise masses at which they occur remains an active area of research. The signatures of collapse also inform galactic evolution. Each supernova injects heavy elements into the interstellar medium, as well as energy and turbulence. This enrichment and stirring influence subsequent star formation, shaping the structure of galaxies. Supernovae also accelerate cosmic rays' high-energy particles that travel through the galaxy and eventually reach Earth. These particles are thought to be energized by shocks in expanding supernova remnants. Thus, the signatures of collapse extend beyond photons and neutrinos to the very particles that pervade the galaxy. Type Ia supernovae with their thermonuclear origin provide their own distinct signatures. Their uniform light curves allow them to serve as standard candles for measuring distances. Their spectra show silicon features and a lack of hydrogen. Their contributions to galactic chemistry differ, producing large amounts of iron group elements. Observations of galaxies across cosmic time trace the combined signatures of both core collapse and Type Ia explosions, building a complete picture of how elements accumulate and galaxies evolve. Open questions remain. How exactly does the stalled shock revive in all cases? What is the equation of state of nuclear matter inside neutron stars? To what extent do magnetorotational effects or binary interactions alter explosions? What fraction of our process elements come from supernovae versus neutron star mergers? These questions drive ongoing observations and simulations. Each new detection, whether of a neutrino burst, a gravitational wave signal, or a peculiar light curve, adds data to refine understanding. In reflecting on the signatures of stellar collapse, the picture is both broad and precise. Light reveals the composition of ejector neutrinos probe the hidden core, gravitational waves trace asymmetric motions, remnants preserve debris, and compact objects embody the final state. Together, these messengers provide a multi-layered account of how stars end their lives. The processes unfold invisibly deep inside the star, but their imprints radiate across space and time, accessible to careful observation. At this final stage of explanation, the collapse of stars is not only an end, but also a source of knowledge. Each observed supernova, each detected neutrino, each mapped remnant is a fragment of evidence. Combined, they affirm the framework of stellar physics that gravity drives collapse, quantum pressures resist neutrinos, mediate energy, and explosions disperse the elements. The signatures are diverse, but they all point to the same central truth that the lives of stars are governed by physical laws consistent across scales, and their deaths enrich the universe in both matter and information.